will wait for 2 more minutes and then I'll start the session. Okay, it's already 6:03. I think I'll start the session and invite students can join. Uh, my audio is clear, right? And my screen is visible properly, right? Okay. I assume that my audio is audible properly and my screen is visible. I'll be starting the session. Okay, thank you. Okay. Today, this is the NPTEL problem solving session for the advances in welding and joining technologies. The course tutor is Professor Sarubag, and myself, teaching assistant Sri ADC. And this is the fourth live session. Today, I will be discussing the third assignment of this year and last year's third assignment. So basically, it's like a solid state welding process regarding solid state welding process. For your information, I am telling like these sessions will be recorded and uploaded in the YouTube, so that it will be uh, uh, accessed, so that it is given to the access to the students, so that it will be useful for students to solving the like assignments questions, and also in exams related to these topics. Okay, then I'll start the session. The first 10 questions will be from the last year's assignment, and next 10 questions, those recently you guys have solved and submitted those questions. So, first question was like using the using the mati- using the material properties of magnesium provided as the modulus of elasticity E is equal to 45 GPa and density is 1700. Calculate the sonic velocity of the material. If you have basically this problem is comes under explosive welding, right? Because of the explosion, the flyer will collide with the substrate. During that collision, the jetting action will take place. Jetting in the sense, oxide removal will be happening, and once jetting is happening, and also the two clean metal surfaces will get joined because of the heat generated due to the collision, and the collision will be the flyer will be moving this sonic velocity. So here the question is calculate the sonic velocity of a material. I hope you guys know the formula, which is basically straightforward. The sonic velocity is equals to square root of E by rho. Square root of V by rho. So E is given as 45 GPa and 1700 kg per meter cube. So one more thing is uh, like 45 GPa gigapascal is given. So we need to convert it into SI units and then we need to solve the problem. So if you, after converting it to converting it to a SI units and if we solve, we'll get the solution as 5145 meter per second. So answer is A. E 45 into gigapascal and giga means 10 power 9. 45 into 10 power 9 divided by 1700. If you take the square root of that, we'll get 5145 of the sonic velocity. Uh, this is also straightforward question. Like which of the following is not a phase of friction stir welding? As we know, in friction stir welding, initially there will be a material and plunging will happen. Once the sufficient plunging depth is achieved, there will be a dwell time. Once the dwell time is done, then dwell time in the sense material will be at the tool won't move, the friction stir welding tool won't move, and it will be at this stationary position. Once the dwell time is done, there will be a welding motion like this. Because of that, and it will be rotating like this, and it will be moving because of the frictional heat, because of the friction, heat will be generated, and with the help of that, we will be getting the wet. That is the in brief, right? So, in the figure, I can observe that this duration is plunging. So, surface, contact surface will be increasing as it is shown in the y-axis, right? Because we are giving only to a downward motion only, no transfer direction motion. There is no welding and all. After that, we will hold for some time. That is called initial dwell. Once the dwell is done, we will move the tool in a transfer direction to get the welding. And once the final welding is done, we will wait for some more time as a final dwell, and we'll plunge it. Once it is moved, we'll plunge it out, and we will remove this, and desired thing will be achieved. So guys, based on this, obviously detonation velocity is under explosive welding, right? Obviously there will be a powder and explode, and because of that, detonation will comes under explosive welding. So what is the question? Which of the following is not a phase of friction stir welding? So obviously the detonation velocity. If you have any brains, you can go through which as well. Okay, I will proceed further. Again, one more problem in friction stir welding. Last time we did an exposing, now it's in friction stir. In friction stir welding of steel plates of yield strength, the tool rotates at 900 rpm and have a shoulder diameter 14 mm and pin diameter of 6 mm. The rate of heat generation on the solder surface due to sticking condition. Here they have clearly mentioned sticking condition. So it like we need to generate the total heat generated due to sticking condition only, not sliding or overall heat generation. So this is the catch here. So sticking condition is there. So we need to apply those formula. Means actual formula is like Q is equals to 2 pi omega tau contact means shear stress contact into RS cube minus means RS in the sense radius of the shoulder, RS cube minus radius of the pin cube divided by 3, whole divided by 3. So mainly that tau contact will change based on whether it is sticking condition or sliding condition. For sliding condition, tau is equals to mu p. For sticking condition, as explained by sir, it is like directly given by the sigma y by root 3. So, this is the formula. As I said earlier, this is the main formula. 2 pi omega tau contact divided by 3 rs cube minus rp cube. Here, tau contact is like based on the condition whether it is sticking or sliding, it will change. Since here sticking is given, so sigma y by root 3. And we know that omega is 2 pi n by 60. N is given as the rpm, so we need to convert it into SI units. So divided by 60 we are doing. So can get into second RPS, to convert into RPS 2 pi n by 60. So it is in the SI unit. Then sigma y is given as 360 MPa. So sigma 360 by root 3. And here we are using MPa means Newton per mm square. So we need to use rest of the units in mm only. So because of that, radius of this thing, the radius of shoulder and radius of the pin should be 14 mm and 16 mm, right? So its diameter is given. So diameter is given. So we need to reduce it into radius divided by 2, 7 mm and 7 cube minus 3 cube as per the formula. The, here, since we are using it in Newton per meter cube, so per meter square, sorry. So here also we should use the radius as that only, like that only. So finally, after substitution, we will get the solution as this 12.96 kilowatt. So answer is 3A. Okay, there are no any queries. Okay, I will go for our next question. And also, uh, after completing these sessions, as in last class also, I give some little basic idea about the how laser and electron beam and also arc beam, arc welding is used in additive manufacturing. Since today we are discussing about solid state welding, and I will give few insights of the where solid state welding mechanisms are used for additive manufacturing, metal additive manufacturing. So you guys will get a little insights into that. So next problem. Again, the flyer plate velocity is 660 meter per second, and detonation velocity is now here he has given detonation velocity also and flyer plate velocity. Find the dynamic bend angle required in case of explosive welding. So you need to know the relation of that. Basically detonation velocity is related to the explosive density of the explosive powder. On that we will get the detonation velocity, but here detonation velocity is already given, so no need to use this relation. And flyer plate velocity, and this relation will use the relationship between the flyer plate velocity and the detonation velocity, uh, and also the bend angle. Since we know Vp and Vd, with respect to this, we can directly calculate the beta. And also, you need to take care of sine inverse and all during the calculation. Uh, Once you do sine inverse, if you are using whether you are doing it in radians or degrees, that also important. Uh, Generally in calculator, you can need to use the proper thing, or else if you get the result in a radians, you need to convert it to 180 degree by pi to convert it into radians to degrees. So based on that, we will get 4.20 degree. So answer is 4A. Basically these are like if you know the relations, we can if you have correct proper relation, if you know the relation, and if you don't, if you systematically substitute the values based on the units, and if you take care of the units properly, then you won't land up in any wrong result. You need to take care. You need to know the relation, and also you need to know the proper uh, which units we are using. Okay, next question is which of the following welding process observes a temperature of more than melting point of the workpiece. So this is like till this is 3 weeks sir has explained about the uh, answer is C. Yeah, yeah. Why? Because this is fusion welding sir has explained in the week 1 or week 2 fusion welding. Week 1 fusion welding, right? Week 1 and week 2, then solid state welding. That is the main thing, right? Like in fusion welding, the material will melt, and also electrode, if you consume electrode, that is also mentioned, coalescence will happen and joint will be formed. Uh, so in fusion welding, what are the various types of welding process will come is like TIG welding, like function inert gas welding, metal inert gas welding, and also submerged arc welding, and also electron beam welding, like high energy beam welding process like electron beam welding, laser beam welding. Uh, those things, and also stick welding, in those fusion welding process material will melt. So obviously to melt, temperature should be more than melting point. So option is as one of you said, option is C only, because here temperature generated is more than the melting point of the workpiece. Another thing is the solid state friction stir welding, ultrasonic welding, and also diffusion welding. This comes under solid state welding, so it won't yeah, the temperature is less than the melting point temperature. Now one more problem in electromagnetic pulse welding process they have mentioned. The force generated between two constituents while carrying a 75 amperes with a separation gap of 0.1 meter gap, and the permeability of the space is 4 pi into 10 power minus C Henry per meter. This is also in SI units, this is also in SI units, and current is also in SI units. All we need to find is force required. Uh, and based on the law, we have direct relation, right? The force between infinitely long parallel conductor is given by, it is directly proportional to I1 into current carrying through the conductors, and also inversely proportional to the distance between gap between them. Uh, so the relation is given as pi naught divided by 2 pi d into I1 I2. So if this, since everything is in SI units, you can directly, no need to worry about the any conversions or anything. So we can directly substitute here. This D here, it is mentioned like 0.25. Actually, it's wrongly printed. It is zero point 0.1. Here it is substituted as zero point 0.1. Once after substitution, we will get as 0.01125. So answer is A. Then consider the following statement regarding the dissimilar friction stir welding. A secondary heat source is used to preheat the harder material, because in hybrid friction stir welding, generally, as I earlier explained, in friction stir welding, there will be a tool, uh, and the tool will be plugged and weld time will be given. After that, because, and it will be rotating, and it will be moving because of the frictional pressure and frictional force. Heat will be generated, that is used for frictional heat is generated, that is used for joining the metal. But it is basically, as discussed in the class, it is basically invented for softer metals and all, like aluminum and all. But in later, for hard materials, they started using this. So because of that, sometimes hardness of the tool should be more, and also if dissimilar joints or if very harder materials needs to be joined, then you need to go for hybrid friction stir welding. Hybrid in the sense, a secondary heat source like any arc or plasma uh, can be used. So the question is, a secondary heat source is used to preheat the harder material because adequate metal flow is ensured around the around the two. Yeah, this is true. It enhances the formation of large amount of metal intermetallic components. Can anyone comment for this question? Seventh one. Actually, the purpose of using this also is to reduce this, right? So this is false. So statement one is correct, and statement two is incorrect. So 7A is the answer. Okay. I will go for next question. Which of the following is not the process parameter of ultrasonic welding? Basically, in ultrasonic welding, uh, there will be sonotrode, it will be vibrated, and the frequency will be ultrasonic frequency, means around 20,000 to 50,000 kilohertz. It will be rotating. It will be vibrating because in that frequency it will be vibrating. Because of that, heat will be generated and welding will be happening. So obviously, ultrasonic power is the one of the process parameter. Clamping force means downwards there will be anvil and all clamping needs to be used. So clamping force is also one of the process parameter. And also welding time, how much time we are carrying out is also important. This tool travel speed basically in friction stir welding, right? So 8C is the answer. That's what we have mentioned. Like what are the process parameters like ultrasonic power, clamping force, welding time, as I said, frequency, and also I mentioned about the linear vibration, but linear vibration amplitude, at what vibration amplitude we are vibrating, are the different process parameters ultrasonic welding, and this tool travel speed mainly the process parameter in friction stir welding. Like in friction stir that will be rotating and how much speed it is moving. Because of that also the frictional heat generated will vary. So 8C is the answer. Next question. Consider the following statement regarding the explosive welding. The jet formation has no effect on the joining of metals during explosive welding. The jet is a product of collision of two metal surfaces. Can anyone comment on this? Okay, I will only tell. Basically, jetting phenomena occurs at the collision point, which basically there will be oxide layer and contaminant surface. Contaminant surface will be is easily removed. This oxide surface, because uh, because of the collision, because of this collision, the oxide surface will be removed. Uh, so it leaves only clean metal surfaces to get in contact, so the joint will be happening. So this phenomenon is called jetting, removing the oxide layer because of the collision and all. So someone else Vivek has texted us C. Okay, let us see. So that is a jet formation. That is a jetting phenomenon. So we'll see the first sentence, whether it is true or not. The jet formation has no effect on joining of metals during explosive welding. No, actually this is false, right? If the jetting is not proper, then the oxide layer will be inside, will be in the flyer also. So because flyer and the substrate, so you may end up with the welding defect. So jet formation, proper jetting needs to be achieved so that joining of metal will get the sound wet. Uh, the jet is a product of collision of two metal surfaces. Yeah, this is true. So for ninth question, yeah, statement two is correct and statement one is incorrect. That is the explanation here. Like as I explained now, during the explosive welding, due to a collision of layer plate, a high pressure pulse is generated. Uh, this pulse propels the flare at higher velocity. This will move in the sonic velocity. Uh, the collision of two metal surface results in formation of jet. That's what removal of exit layer and clean metal surfaces will be there. So jet forms allows two metallic surfaces to join under extremely high pressure. So as I explained, so B is the answer. Uh, I think sir has taken more than one class to one session to explain the friction stir welding. I think you guys, any of you can give a solution for it. Can comment on this for the solution for this. Which of the following factors? I'll read the question for you. Which of the following factors is responsible for producing a proper weld during frictional stir welding? We need to get a proper weld. So, like D, appropriate material flow and proper, yeah, because our tool geometries, like we know, right, tapered tool, cylindrical tool, threaded tool, and in which material we need to decide for which material we need to use corresponding tool, proper tool. So proper tool geometry selection should be there, but so here they have mentioned like improper, so this is not the like if you use improper thing, then we'll end up with a bad bed. So and also that plunging is also an important thing, so that proper contact surface will be there between the shoulder and also the tool pin. So we can achieve the required heat to get the weld properly, and also gap should be less. So as you said, D is the answer. So proper tool geometry selection, sufficient plunge width, and these are the mentioned here, like sufficient plunge and minimum, as I have explained. Appropriate material flow selection and proper heat generation are some factors responsible for producing a good weld quality. So 10D is the answer. Okay, I'll go a little bit fast. These are next. You guys have solved these questions. I hope you will answer it well. And also, if time permits, I'll give few insights of the, as I said earlier, the insights of the additive additive manufacturing techniques where solid state welding is used. And also, uh, for sake of continuity, I'll also explain where laser, electron beam, and arc beam welding is also arc welding is used. So I'll go a little bit faster. Select the incorrect pair of welding processes and their bonding mechanisms. So basically, explosive, explosive friction stir welding and also ultrasonic, there will be localized melting. So, but here ultrasonic welding they have mentioned like diffusion. So this is not true, right? So this is the incorrect pair. Yeah, Vivek, it's correct. B. Yeah, 11B is the answer. In which of the solid state welding, in which solid state welding, bonding mechanism grain bond in nitration occurs? Interfacial morphology. Okay. Actually, based on the morphology between the surfaces, interfacial means interns between the surface. What is the morphology? Is that morphology will be dominating in the providing the weld joint. That is basically interfacial morphology. That is called interfacial morphology. I right now I can't tell much about this. If required in next session, I will give little details. And also, I forgot to tell one more point. Sorry for I thought of giving in because as it started in solid state welding we go generally to avoid brittle intermetallic compounds, right? Uh, so next class maybe I'll give some example uh, if you do aluminum and steel welding, so what kind of intermetallic compounds will be achieving, so will be formed, which are adverse to the welding, so which we need to avoid. Basically, today I forgot to keep that slide. Maybe next class I will explain about this intermetallic concept. What are the intermetallic? And I'll give you one actual example in aluminum steel, how the intermetallic compounds influence the like the quality of the welded component. Next session, I definitely put this intermetallic components for the sake of understanding. So we were in, right? Yeah. This, as explained by Sir, grain boundary migration occurs in recrystallization. This diffusion is thermally this thing. Interfacial means between the surface reactions. Because of those things, this A and B will be there. So B is the answer. Okay. Basically, the mechanism in diffusion is like because of pressure and elevated temperature, the bonding is happening. There won't be any like grain boundary migration and all. Mainly, it is in recrystallization. Okay. Okay. For cold welding process material, should have good, yes, ductility. Yeah, see ductility, correct. In next class, if you want further clarity about diffusion and all, I will try. If time permits, I will explain in the next class. But if you go through this third slide properly, he has mentioned properly. He has discussed that in that slide. For cold welding process material should have obviously here we are not even applying temperature, and just with the help of forging, if this is the metal to be joined, if this is the metal to be joined, so I will be like cold, like I will be applying the forging force. So if it is better, if it is ductile material, then better also deformation and all happens. So because of that, joining will happen. So it should have good ductility. So that is the main thing. If work hardening is there, means again because of work hardening, the strength will increase. So the ideal weld, like proper weld, we won't achieve. So these are thermal related properties. We mainly concerned about the ductility of the material in cold welding. So C is the answer. Okay, next 14th question. In which of the following welding processes no heat is applied for welding? I hope if you guys can anyone comment? I'll tell you the answer. 14C is the answer, like ultrasonic and cold welding. This in diffusion and explosion, like the heat will be applied. Because in explosive, okay, wait for a minute. Someone, yeah, C is the answer. In ultrasonic welding, mainly because we are uh, we are vibrating that sonotode in the ultrasonic frequency. Because of that, frictional heat is generated and welding will be happening. That is the thing. In cold welding, just now I explained, metal will be there, forging kind of thing will be done, and will achieve the cold welding. In diffusion, it is mainly like in diffusion welding, mechanism of cold welding. Okay, actually, I thought like since those were explained in class, I thought like I kept few slides for additive manufacturing, how we can use this for solid state welding and additive manufacturing. If you explain those mechanisms in next class, right now I don't have diagram. Basically, the thing is like there will be two plates, and we'll apply forging force. Because of that, joining will be happening. With diagram possible and time permits, next class I will explain that. And in diffusion bonding, again, since you asked, will apply a force for a long time, and also will heat the surfaces uh, to certain temperature. Because of that, we'll achieve welding. We'll apply the pressure, and also will heat the uh, workpiece material. Because of that, we are achieving the welding in diffusion weld bonding. So that is in diffusion bonding. In explosive, we will use detonator and we'll use the and it will get detonated and supersonic velocity. With the help of the detonation velocity, the momentum will transform, and the flyer will move in a sonic velocity, and it will hit the substrate, and heat will be generated, and welding will form. So here also for detonation and all, heat is used. So as we said, C is the answer. Okay, fine. Okay. Which of the following material is used for sonotube and anvil in the ultrasonic welding process? Uh, one more thing. Like I thought, these are discussed in the class, so I didn't keep those slides and also figure. So next class I will keep possible. So sorry for that. Which of the following material is used for sonotube and anvil in the ultrasonic welding process to weld high strength material? High strength metals. For the point is like ultrasonic welding, and also for welding of high strength metals. Basically, for ductile materials and all, we use high speed tool steel because it has good toughness. Uh, but for material which is harder than the high speed steel, will generally, as discussed in class, will use uh, hardenable nickel base alloys. So 15D is the answer. Okay, I'll go for next question. Among the following terms, which one is not related to friction stir welding process? This is basically straightforward question. Can anyone comment on this? And you guys have solved this also, right? Yeah. Yeah. Among the following terms, which one is not related to the friction stir welding process? So what you said? When I need to check in chat box. Hmm. Yeah. Obviously, because flyer is used in explosive welding, right? The flyer substrate combination and also detonator is used. So this flyer will come in the explosive welding. This advancing side and also retracting side, spindle speed, like how with what velocity we are rotating the spindle, with what velocity we are rotating the spindle, and also tool geometry, as like whether we are using threaded portion of the tool pin, or we are using cylindrical portion or tapered portion, or taper threaded thing. So that is also an important thing. So this flyer will be the answer, is not related to friction stir welding. Next question is, identify the correct pair of welding process and terms associated with them. Actually, this is also correct pair of welding process and terms associated with them. Okay, I will discuss. Like explosive welding, obviously jetting is happening, so explosive welding is there, and also electropulse welding. There won't be any sonotrode, right? In ultrasonic, sonotrode will be there. So 17.2 is not the case. The second option is not the case. In friction stir welding, uh, advancing and retreating side is there. Yeah, so this is also true. And next, in cold welding, forging force. As just now I explained, forging force will be applied. Uh, so this is also there. In In ultrasonic welding, eddy currents, not at all, right? In ultrasonic welding, uh, in electric pulse welding, eddy current, and those things will be there. This is also wrong match. So answer is 17A. This is also a straightforward question. Fill in the blanks by selecting the appropriate option in the sentence. Appropriate option in the sentence below. Basically, the question is from diffusion welding, right? Uh, in the diffusion welding, in diffusion bonding process, joining is achieved by application of yeah, uh, yes, C is the answer because first we'll apply the pressure and will maintain that pressure at the elevated temperature to get the diffusion welding process, diffusion bonding. So C is the answer. Due to which reasons friction stir welding can be referred as green technology. So the time in friction stir welding, the process will directly use one FSW tool, friction stir welding tool, and which will be plunging. Will plunge it. Will wait for bell time, and then with the help of spindle speed, will move the travel, give the travel speed. Because of that, welding will happen. Here we are not using any shielding gases. Like also uh, so, so it is environmental friendly. So the question is like due to which reasons the fixed steel welding can be referred as yeah due to yeah we correct due to which reasons the friction stir welding can be referred as green technology because it is energy efficient compared to other welding process. All we are supplying is uh, electrical energy, those things, and it does not produce any kind of gases during the welding process, hence it is environmental friendly. So just now, sir, now I explained. Uh, Due to its capacity of joining dissimilar metals, this is a different context. So because of this, we won't tell that this is a green technology. And also, fifth is also not. It is valid for friction stir welding, but not for this statement like why it is called green technology. So 19A is the answer. So last question. Select the correct set of process parameters for the electromagnetic pulse welding process. Electromagnetic pulse welding process. Inductor center circuit, yeah, it will be there. Electromagnetic pulse tool geometry, no, it's related because it is related. Tool geometry is mainly related to friction stir welding. Uh, then that clamping force is also related to friction stir welding, but the frequency, yeah, it is related to the electromagnetic pulse. So 1 4 is correct, and also simultaneously like current is also in one of the factor, and voltage also. So 20B is the answer. These are some theory questions for this assignment, third assignment. So little bit time is there. So I'll give how the solid state welding process using additive manufacturing. I'll give you I'll discuss briefly about these things so that if you guys have interest, you can get like study further in those things. Basically, AM process. This I already have explained in this last class. Basically, additive manufacturing process. I know. Hopefully I know. I think that you guys know the definition of additive manufacturing. Basically, additive manufacturing means it's converts to the subtractive manufacturing where it is like we'll removing the material or forming techniques where we'll be with the help of die combination we'll be using some kind of compressed force or some kind of tension force will will form it and will get the component. that is in metal forming. In subtractive medium, we'll remove the material. Whereas in also in casting and all, we'll melt the material and we'll pour it in a die, and we'll get these things. These are all conventional things. In additive manufacturing, we'll based on the CAD model, and based on the CAD model, we'll deposit the layers uh, we'll deposit the layers so that layer by layer we'll deposit to achieve the component based on the CAD model. So here all we are dependent on CAD model and slicing techniques. Some concept is there like slicing technique. Based on that, we generate based on the slices, we generate the tools. Once the tool is generated, we can we'll deposit in the component. So basically, here this additive manufacturing is not specific tooling. Tool is immaterial. So that is one of the advantage. There is no part specific tooling is there. In conventional, suppose if I want to cast or form, so particular tool die combination we need to take. Uh, so it is like part specific tooling in conventional thing. Here there is no such thing, and also customization since it is uh, since it is not dependent on any tooling or anything, and it's only dependent on digital format where we'll generate the tool path. After that, we'll give the tool path to the deposition head, and deposition will deposit based on the CAD model information, and will deposit layer by layer. So that is additive manufacturing. So based on the feedstock, basically we'll use feedstock right in additive manufacturing to deposit layer by layer. So if the feedstock is we classify based on the feedstock condition, based on the feedstock, we'll classify it as liquid based, solid based, powder based. Uh, in liquid based vat photo polymerization, here basically in the container we'll have a liquid, and we'll with the help of laser power source, as discussed in the last class, with the help of laser power source, uh, it will whatever the tool path is there, it will travel, and it will because of the laser power source, the material gets reacted, and basically it will get solidified, uh, and we'll get the layer component. After that, again we are uh, again we are changing the position either with the help of platform, or with the laser focusing. Again we'll use the based on slice information. Again, this process will repeat it from first layer to the nth layer to get the component. That is liquid based vat photopolymerization. So solid based FDM, here there is some kind of filament will be there. Based on the resistant heating, the material will be melted and will be deposited as required to the CAD model, as per the CAD model. So, and also sheet stacking technologies. So here where we use this today, as we explain discussing about the solid state welding, those things mainly used in this sheet stacking technologies. So this is where this application is there of solid state welding along with the welding. Also in additive manufacturing, metal additive manufacturing also we can use sheet stack technique, and also powder based is also there. In powder based, we use laser and electron beam to melt the feedstock, whether we can feed directly or some kind of powder bed will be there. On that we will be directing the power source as per the slice information. In this slide we can see the, as in last class I have discussed about these things. Here powder bed, based on the slice information we'll have the we will move the laser as per this slice information. Once for one layer it is moved, again this platform will be moved downwards, and with the help of this rotating roller, will again spread the powder over the build platform, which is already which we brought down because after one layer of deposition. So fresh powder will be spread over the platform, and again the based on the slice information, this laser is used, and because of that again will get because of that melting will happen and coalescence will happen, and there are other many bonding mechanisms also there. Some kind of sintering is there. Many bonding mechanisms are there. Based on that. Mm, based on that we'll achieve the required component. That is powder bed fusion. This basically SLS, selective laser sintering process. This schematic basically shows. And in next thing, uh, direct energy based deposition process. Here we can use laser or electron beam, and powder will be fed directly. That's why it's called direct energy deposition. Powder will be directly fed to the laser or electron beam, and based on that it will get melted and it will get bonded, and layer by layer deposition will be there. So this is the first layer deposition. This is second layer deposition. This is third layer deposition is happening in this schematic. Since we are using powder and all, handling of powder is very difficult, and also um, manufacturing of powder is much more difficult, and also pow- and powder particle size is also very less. So we can use it only for media, like small sized components. And also, but one advantage of this powder thing is like either it in powder DED or powder bed fusion. You can use it for complicated shapes of metal additive manufacturing. But if I want to deposit a uh, medium to large size components with medium complexity, then we can go for arc welding. And also this setup is also very uh, as we know in arc welding it is very cheaper compared to electron beam welding setup or a laser beam welding setup. So we can customize the arc welding setup to additive manufacturing. So in this figure it explains about the schematic diagram of the GMAW based AM process, where arc will be there, and we'll be depositing layer by layer based on the slice information. The electrode will be melting and it will be deposited as per the movement of the torch or the movement of the substrate. Movement of the substrate in the sense, sometimes we'll use work moving table. In some other cases, we'll uh, we'll attach this torch to the robot, which has 6 or 5 degrees of freedom with the help of our gantry based system. With the help of that gantry based or robotic manipulator, will be moving the GTAW or GMAW or plasma torch, and based on that, we'll be achieving the required component. This is GMAW based process, and the process is called wire arc additive manufacturing process. Generally, it's used for medium to large size components. And also, since we are using arc based welding, deposition rate is also higher because here powder and all is used. Here wire is used, and handling of powder is a wire is also easier compared to powder. So this is one of the advantages. So next comes the uh, this sheet tacking techniques, like it's called as laminated object manufacturing. Basically, what happens is like we'll take a sheet. Uh, there are two classifications in this. Basically, I explain only one as shown in the figure. So basically, we'll cut the based on our required slice. We'll cut the sheet. As you can see here, with the help of laser process, we are cutting the sheet. Once cutting is done, we'll do it for all layers. So we cut the sheets layer by layer from a given sheet thickness for a given sheet raw material. So once it is done, we will stack it one over the other as per the sequence. Uh, Layer 1, layer 2, layer 3, layer 4, like we will stack it. Once it is stacked, it needs to be laminated, right? So for that, we'll use, as we discussed today, as discussed in the solid state welding techniques, like we can use adhesive bonding, thermal bonding like diffusion, clamping also can be used with the help of some kind of fastener, and also ultrasonic welding can also be used. So see, if when I am staking, if I use some kind of adhesive, the adhesive bonding with the help of adhesive, the sheet metals will get joined, and further some furnace treatment needs to be given, so that we'll get the some sintering will happen after that furnace treatment. So we'll get the proper bond. That is adhesive bonding technique. And thermal bonding means, as we know, diffusion bonding, we need to apply the pressure and we need to maintain we need to maintain the load for that temperature. Mm. So that is thermal bonding process. And also, without, okay, if you don't use adhesive bonding or thermal bonding, you can directly clamp it. If our application permits it, then we can use bonding mechanism clamping also. Finally, in this figure, uh, ultrasonic, even friction stir additive manufacturing is also, friction stir tool also can be used here it is not mentioned, and also ultrasonic welding. So whatever you learned in welding this course, this basically we can apply it to the additive manufacturing, which is a booming technology, which has a large scope, especially in the metal additive manufacturing. So if you thoroughly understand this process, you can directly correlate these techniques to additive manufacturing. Uh, so in this ultrasonic welding is there. Uh, so as we know that rotating sonotode, because of that friction will be generated, right? We'll stack the layer by layer or sheet by sheet, and with the help of sonotode, we'll be moving because of that friction. Because of that heat will be generated, and we'll get the uh, that sheet and sheet will get joined. And after that, again, based on this slice information, again I'll stack one more sheet, and again I will use this ultrasonic sonotone, and I'll get the joining. This was explained in this figure. Similarly, if I use friction stir nowadays, even the usage of friction stir welding is also picking up the pace, and with the help of that also, because one of the major advantage in friction stir and the solid state welding is like dissimilar joints can be joined, right? So that we even you can achieve functionally graded materials. Functionally graded material in the sense, the properties of the materials, we can change properties accordingly from the along the component, either it is compositionally we can change, so that we can achieve the required application. If you just google it about the functionally graded materials and its application, you will get to know what is significance and all. So with the help of solid state welding mainly, we can achieve easily the functionally graded friction state welding, and this the solid state welding, you can functionally graded materials can also be 3D printed. So this is about this today's class.